Hello everyone, I am here to present lecture based on transient on transmission lines. So this topic comes under module 2 symmetrical fault. So basic question we have, why they kept this transient on transmission lines in this module 2 symmetrical fault. When fault occurs, then only transient will occur, right? So in the transmission lines, for example, I'll tell you. So if suppose tree branch is falling on the transmission lines, what happens? Automatically short circuit occurs. It may be a triple L. If suppose tree branch touching both, like all the three wires, that is triple L, and then the tree is touching to the ground, that is triple LG fault. If suppose the tree branch touches with only one line and then the ground, that is LG fault. So similarly LLG fault will be there, LL fault will be there. So if suppose birds, bats or whatever, so if touches two lines, so we will get LL fault, and then insulation failure also will be there. If suppose failure in the power supply, failure in the any electrical power system components, power system switch gears, so we will be having a faults. So here in this module we have some basics also. So we need to discuss basics also. So we have with us there is a short circuit calculation. So we already discussed in the first year as well as second, third semester basic electrical circuit analysis concepts. So transient of series circuit, parallel circuit, we already discussed, right? So based on that, I'll be giving some basics, and then after that I'll get into the syllabus. So I'll be considering one I'll be considering one circuit here, the RL series circuit. So he's having EFT is the supply voltage, and the RL are the impedance in the transmission lines, and the switch will be there, right? So when T is equal to 0, so this implies when T is 0 plus, that is after the fault, and T is equal to 0 minus, that is before the fault, and T is equal to 0, so at the particular time of fault, right? So this is a one basic circuit diagram, so we'll be having. So we already discussed in the basic electrical, we derived the equation also, RMS value, average value of the AC components, and then when resistance connected across the supply and the inductance connected across the supply, as well as RL circuit. RL circuit we discussed basically in the first years of engineering. So here I choose the RL circuit. So because transmission lines is having a RL series circuit, number of RLs will be there, and the number of capacitor is connected over there, and several type of electrical parameters will be there. So the supply voltage V is equal to Vm sin omega t, that is V of t is equal to, this is a time constant, okay? So time t is the time, V is equal to Vm sin omega t plus alpha I added here because so I have taken pre-fault, before the fault, alpha I added, and then V max into sin omega t plus alpha, how will get? So Vrms is equal to Vm by root 2, so that is root 2 into Vrms is V maximum voltage, right? So this is so maximum voltage, this is maximum voltage, sin omega t plus alpha. So next step, if I apply a loop, a KVL loop for this circuit, what we will get? So this is a voltage, supply voltage is equal to drop across R and then drop across L, inductance, right? And T is greater than equal to 0. So V is equal to Ri plus L into di by dt by applying the KVL loop 1, okay? Loop 1 or whatever you consider. So there is a switch will be there. When switch is closed, that is fault. So just example I'm giving. So if suppose if suppose it is observed in the transmission lines, if it is related to transmission lines, so if suppose switch is closed, that is fault, and then switch is not closed, that is T is equal to 0 minus, before the fault, and T is equal to 0 plus after the fault. So these are the concepts we have. This is a basic, okay, basic. So after integrating the equation, we'll get the equation like this: I of t is equal to Vm by z, I mean V max by z, sin omega t alpha minus theta, and then e raised to minus RT by L sin alpha minus theta. This we can see while deriving the equation of RL circuit. And then this one is DC offset current, e raised to minus t by tau. T is the time constant, that is tau is equal to L by R. And then sin omega t minus theta. So already we discussed in the basic electrical concepts, I is equal to Im sin omega t minus phi for the RL circuit, I is equal to Im sin omega t plus phi for the RC circuit. Current leads by voltage and then current lags by voltage at an angle phi in the RL circuit. So this is the impedance, everybody knows, R plus j omega L square, or R plus j XL, and then theta is equal to tan inverse of omega L by R or XL by R. This is a phase angle. So if the fault current, if you want to find out, we will get I of t is equal to addition of, I mean sum of IAC component and IDC components. If suppose suddenly fault occurs in the transmission lines, you will get AC components as well as DC components, DC offset components. If suppose, for example, I am telling you, if suppose tree is falling on the branch of, tree branch is falling on the transmission lines, I mean it's having transmission lines like here to here, one pole will be there, and then there is a transmission line. If suppose tree is falling, so what happens? There is a fault occurs. What happens? The current will be rises extreme level. So that is a fault. If suppose current reaches extreme level or higher level, what happens? The automatically the current increases some level. So automatically the wire will get damaged, or circuit breaker will be there for safety, but fault will occur. So this IAC is the AC components when fault occurs. IDC is the DC offset component, I mean the DC offset current when fault occurs. It dies out. DC components will dies out. I mean like it will be decaying. Like e raised to exponential will there. This is this one. This part is this one. So an AC component. So I of t is a total symmetrical fault current. Okay. And so this is a waveform which I have seen already. This is AC components. The positive will be more compared to AC, and negative, and then this is here. So it will be slowly decaying, and then so it increases. If suppose fault occurs here, so it will be increasing suddenly. But DC fault occurs here. Okay, fault occurs here. What happens? It will be increasing slowly, and then the DC components slowly it will be decaying, I mean dies out here. So this is IDC, and then this is I of AC, this is IT. So this IT is equal to addition of these two, we will get fault current. So this is a basic we should know while discussing, while deriving the equation. So let's move on to the syllabus. We have okay, transient in transmission lines. Before itself I told there is a switch will be there. If suppose switch is closed, that is a fault. Okay, so this is a transmission lines having R and X. R is the resistance, and then X is the inductance, inductive reactance of the transmission lines, that is the impedance. If suppose fault occurs in this particular point, what happens? The voltage will be E is equal to Em sin omega t. So initially voltage will be Em sin omega t. Current will be, I mean before the fault. Okay, before the fault. So Im sin omega t minus phi is the basic common equations already. This is a basic. Okay, it's a basic. So when t is equal to t naught, so next now we'll start our concept of fault occurs. This is basic. These two are basics. V is equal to Vm sin omega t, or E is equal to Em sin omega t, I is equal to Im sin omega t minus phi. It's a RL circuit equation, current equation. If suppose fault occurs, omega t is equal to t naught, I mean t is equal to t naught, fault occurs, what happens? I t naught is equal to omega t naught minus phi. So I replace t into t naught. So take omega t naught is equal to alpha, phase at the time of the fault. I mean at the time of alpha the particular, I mean before the fault. So omega t naught is equal to alpha. So we will get fault current as I of t is equal to I suffix of s, I suffix of t, steady state current. This is a AC component. This is a transient current. When during the fault, transient current occurs, is produced. So while deriving the equation, I mean while getting the equation of I of t, we have transient current decay at the time constant tau is equal to L by R. So RL circuit, time constant is RC circuit, tau is equal to RC, RL circuit, tau is equal to L by R. I of t is equal to, I just substitute I of t, I want to suffix t, I want to calculate, I mean I want to determine. I have 0, I mean 0 initial condition, e raised to minus RL by t. This is RL by t is a time constant, so L by R, em by z, this equation you will get it. So I'll tell you how exactly you will get this alpha minus phi by seeing the diagram, by seeing the waveform. Okay, and I of t is equal to this equation we got. This is a DC offset component. So e raised to minus RL by t is there. DC offset like this, so it will be slowly decaying. So I of t is this one is AC components. This one is DC components. I am sin, I mean I is equal to m sin omega t alpha minus phi, I am sin omega t minus alpha raised to minus RL by t. So impedance will be there, and then phase angle also will be there. Okay. So next we have a waveform. By seeing the waveform, we'll come to know how exactly fault occurs and how exactly. So it will be understand. So alpha I have taken, I told you before itself, alpha I have taken, this is before the fault, I mean this waveform, this wave also I added here. So this is a sine wave component, this is a DC offset component. When fault occurs in a point here, so the DC component slowly it will be decaying, in a sense e raised to minus t by tau, it's a exponential. So I have merged these two waveform into here. We got the waveform like this, and then this waveform, and then this is these two is exponentially decaying and dies out in a sense. DC components will not be there in a longer period, so it will be dies out. If suppose longer period it will be available, in a sense, definitely the whole system will be damaged, and then whole system will dies, I mean lies in a sense, so it will be going down. This is a concept so we discussed previously, fault, and then what are the types of faults, and subtransient, transient, and steady state components, and then this is oscillogram. Suppose sometimes the question paper like this with oscillogram and with a waveform explain transient on transmission also, the last question, so be aware.